Okay, thank you, Dr. Aziz, for sharing the previous two keynotes. So we would like to continue the conference with the first paper presentation session, okay, which is the session number 2. The theme of the session is environment and safety. It will be chaired by Dr. Nur Shazwani binti Muhammad Ali, which is my colleague over here in UTM. Over to you, Dr. Shazwani.
Okay, I hope that you can hear me. Sorry for that technical error. Probably my headphone is not working. So once again, thank you. So we're going to continue our event with second session, which is the first paper presentation from the participants. So for this session, we're going to have 4 presenters from UTHM and 2 from Nuclear Malaysia and another one from University Technology Malaysia. So I think just a little housekeeping before we get started. So if let's say you have any question during the presentation, you can just type your question in the chat box and I will bring them up during the Q&A session. And for the presenter, just to remind you that you're going to have only 20 minutes presentation. And including the Q&A session. So I hope that that's all the housekeeping that I want to mention here. So without further ado, I think I would like to invite our first presenter, which is Dr. Ahmad Hassan Salihuddin bin Muhammad Sarif from University Tenusin On, Malaysia, for your presentation. Over to you, Dr. Ahmad Hassan.
Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Thank you very much to Dr. Shazwani. So let me share my screen first. Can you see my screen?
Yes, sure. I can see your screen.
Oh, okay. So, so my name is Ahmad Hassan. The title of my presentation is Time-Independent Reliability Analysis for a Critical Reactor Safety System based on the fault tree approach. These are my contents, typical contents. So I will start with probabilistic safety analysis. So PSA or PSA, so probability safety analysis or PSA is an important safety assessment tool for nuclear installation, especially for nuclear power plant. Okay. And the main objective of PSA are trying to answer the following questions, which are what are the possible accident sequences, chronologies that can occur at the nuclear installation, okay, and when the accident sequence occurs, we want to know how likely, or what is the frequency of the sequence. And finally, due to the accident sequence, what are the possible undesirable end states that can occur. And for the modeling tools in PSA, mainly there are event tree and fault tree, which we use event tree to identify the possible combination of success or failure of our safety system or our mitigation system in response to the initiation of the accident. And we use fault tree to systematically and logically model the reliability of our safety system or our mitigation system. So PSA has been systematically grouped, and the grouping is called PCA Scope. This is for the systematic classification of the level of analysis. So if you see the vertical axis, that's the level of PSA. We have level 1, level 2, and level 3, and the horizontal axis is the type of hazards that can cause, that can start the accident. There are many involving internal events, internal flooding, internal floods, and so on. And the axis pointing towards ourselves is the amount of the reactor operation if the PSA is performed for nuclear reactor. And if we consider the inner box, which is the level 1 PSA during the full power operation, and the cause of the accident is the internal events. The what should I say? The common hazards that usually thought of is the loss of integrity of the primary coolant boundary, meaning that the reactor is losing the coolants. So the coolant is not only to during normal operation, the coolant is not only to transfer the heat, but it is also a protection for the nuclear fuel. Okay, so when there is a loss of coolant, or let's say a break, the amount of coolant will be reduced, and eventually, if the core is uncovered from the coolant, okay, the core will become the source of hazards. Okay, because we will experience the rise of fuel temperature, and after that, that situation will damage the nuclear fuel core. Okay, that are one of the reason for every plant there is or there are a dedicated safety function, okay, to provide emergency cooling function. Okay. So to recover the loss of coolant inventory, and as well as to provide long-term cooling to remove the decay heat. And so the motivation of this study is to look into the reliability, and specifically the how the reliability change as the time goes by. Reliability of the emergency cooling system at a nuclear power plant. So this involves the failure mode and effect analysis for each of the component in the system. Okay, and then after that, the construction of the port 3 and the quantification of the port 3. For in this particular study, the graphical construction of port 3 and the quantifications are performed using a Spectrum PSA computer software. Okay, we have selected an advanced pressurized water reactor, which is the Korean Advanced Power Reactor 14,000 or APR 14,000 for its safety injection system. And the scenario that we analyzed is the post large break loss of coolant accident. So how does the system, the SIS system, perform during this particular accident condition? So this is the schematic diagram of the SIS. There are 4 trains, namely train 1A, train 1B, train 2A, and train 2B. And each train will inject evaporated water from the IRWST, or the in-vessel refueling water storage tank, during the post large break loca into the reactor vessel via direct vessel injection. Via direct vessel injection nozzle into the reactor vessel. Okay. However, for the success criteria for the long-term cooling after large break loca is that evaporated water must be continuously injected via train 1A and train 2B, because only at train 1A and train 2B, other than through the direct vessel injection nozzle, the evaporated water, or the borated water also injected into the vessel through the hot legs. So from train 1A and train 2B, injected water, borated water is injected through the direct vessel injection nozzle, and as well as through the two hot legs of the reactor. Other than IRWST in the system, there are also safety injection tank. But in this particular case, for this particular analysis, we don't consider the reliability of the safety injection tank. Other than that, there are a series of valve check valve, and also importantly, the safety injection pump. So the methodology involves FMEA, failure mode and effect analysis. So this is to identify and screen out. Identify the relevant component and to screen out the unrelevant component, and then to consider the effect of the failure of each component to the functionality of the SIS system during the post-lunch break locale. And by doing the fault tree modeling and quantification, to model the fault tree, and to quantify it, we use the outcome from FMEA. And then with the fault tree calculated, we can further evaluate each of the contribution from each of the basic event. And then also from the base fault tree, we also try to look at the effect of operator recovery action to the reliability of the SIS. So these are the result of FMEA. So all the components listed here are the components that shown in the previous figure, the previous schematic diagram. Especially for the pumps, there are two failure modes, FTS, which is fail to start, and FTR, fail to rise. And the last column are their reliability parameter. So this is the failure probability of fail to start, and that is the failure probability of fail to run. And sorry about that. And then other than that, the valves, can fail by fail to close or fail to open. And same good for the check valve is fail to open, and we also we screen out the basic components such as RWST, SIT, and pipes. And all the reliability data taken from NORAC document. So this is the constructed fault tree. So the top event is the failure, long-term cooling failure by the SIS. Here, immediately below the top event, there are two intermediate events. So each corresponds to the train 1A and train 2B. So this intermediate event is connected to these three. And after the quantification of the base fault tree, these are the minimal cut set lists that are obtained, especially for time at 30 minutes after the initiation, and the top event. The failure probability of the system is this value, and unfortunately, single failure, and any single failure of the basic event will lead directly to the failure of the SIS. and this does not comply with the single failure criteria. And if you can see the top contributor, the safety injection pump failed to start, but in the long run, specifically at 5 hours, the first two at the top are replaced with still the pump, but a different failure mode, which is the fail to run. Okay, because the failure, the fail to run of the safety injection pumps increasing with time. Okay, whereas other basic event have constant failure probability. Okay, so this is the failure probability of the SIS with time, and specifically at 72 hours, the failure probability increase 6 times. Okay, and again, the same reason, because of the safety injection pumps fail to run. Okay. So we can think of other measures, okay, to increase the reliability of the SIS, such as operator recovery action. I will come to the operator recovery action later. So now let's take a look at the fast basic importance. So by definition, fast basic importance is the ratio of reduced unreliability or ratio of increased reliability when a basic event is completely reliable. It means that it does not fail at all. Okay, and particularly for the pumps, if we can find a way to make it not fail at all, the benefit is 100% increase in reliability. Okay, and for the basic event, their value are not that significant. They are less than 1 per 1,000. Okay, and so the same reason that I explained just now for this outcome. Okay, if we consider a human intervention of human action, okay, so this one, it is found out that the mean unreliability of the SIS decrease by 2 order of magnitude, okay, from 10 to the minus 2 to 10 to the minus 4, okay, by introducing a nominal human performance, okay, 0.011. This is the value from SPAR-H method. Okay, and we can see the minimal cassette now. We can see the compliance of single failure criteria. Okay. So there is no more single basic event that lead directly to the failure of SIS, and now we can see the combination of the human recovery action and the failure of the hardware. So to conclude our works, so we perform the time-dependent fault analysis for the SIS, okay, and a failure mode and effect analysis was inevitable, and we use digital data from similar industry from the new REC document, and the degradation of SIS with time is mainly to the safety injection pump, and with the introduction of recovery action, we can see the reliability improvement, and in practice actually there is a human recovery action, but for the analysis I first commit the human recovery action, and after that I include the human recovery action to see the effect. And however, we omitted many important basic events such as human errors, electrical power failures, basic components, and the electronic of instrumentation and control. We also didn't work on the common cause failure, and we only consider the mean value of the reliability parameter for all basic events. Okay, we neglect the distribution parameter of the basic events. Yeah, I think that's all from me. Thank you for your attention.
Okay, thank you, Dr. Ahmad Hassan, for your presentation. So I think from the chat box we don't have any question yet. So probably to the audience, if you want to ask, you can just write in the chat box so that we can discuss together with the presenter. But since we're running out of time, so I think we need to proceed to the second presenter. Once again, thank you, Dr. Ahmad Hassan, for your presentation.
Okay,
So,
thank you.
all right.